We're going to talk about another differentiation rule that is extremely helpful to us. So far we've talked about how to handle mathematical operations, different types of functions like power functions, rational functions that take the quotient rule, functions that are defined to be products of two other functions. Here we're going to talk about another type of function that we see often, but we haven't really talked about how to differentiate this type of function. And the chain rule is a powerful tool for us to use in finding the derivative. It's a tool we're going to use all the time. So let's talk about, I really want to highlight the idea that we're dealing with the derivative with respect to the independent variable. When we have had a function before defined to be some manipulation on x, the independent variable, when we find the derivative, what we're doing is we're saying the rate at which this function is changing with respect to its independent variable. I could have h of t. When I find h prime of t, it is the rate at which h is changing, the rate at which h is changing with respect to the independent variable t. So the measure of how fast the function is changing with respect to the values of its independent variable. And this has been really straightforward for the functions that we have used so far. But what we haven't done with these functions is we haven't composed them. And when we compose functions, we have to use this rule in order to find the derivative. So for this function is y as a function of u. If I find y prime, that's the change in y with respect to its independent variable u. So given some u value along the horizontal axis, I can look at the slope of the tangent line at that u value and tell you what the derivative is, how fast the function y is changing according to any specific value of u. If I look at this function, here is u as a function of x. When I talk about the change in u with respect to x, how fast u is changing according to its independent variable, which is x. Here I'm going to look at specific x input values, look at the slope of the tangent line at that value, and that's the derivative. I do want to tell you and take time at this point to tell you don't get overly attached. I know I've said this before, but I just want to remind you, don't get overly attached to x and y or even f of x. I try to use these functions and these variables as much as I possibly can when I teach a concept, because then you're not struggling with notation and calculus content. However, when it comes down to the test, there's going to be a wide range of variables used on that test. So don't let a change in variables get you off track when you are applying a calculus concept that you've learned. We still want to apply the steps in the process correctly. So here is a function with an independent variable of x, but there are two functions involved, two manipulations happening on that independent variable. One inside. We went over here, we had domain values of x, and the first thing we did with them was put them in the u function machine. That was some sort of manipulation on them. And that gave us our range value, we'll call it y, or we could even call that range value u of x. And then we take that value, u of x, and call that value a value in the domain, and put that into another function machine we're calling y. And that range value that comes out of that is y of u of x. So this is a composed function, function composition, a composed function with separate behaviors, one mathematical operation on the independent variable inside, and then that result fed into another function machine that performs a completely different operation. In order for us to find the derivative of that function with respect to the independent variable requires the chain rule. So we're going to learn the chain rule for finding the derivative of composed functions. Here we have function f of x. In your notes, let's don't call it f of x. Let's call it h of x. So we have this function h of x, which is defined to be f of g of x. G of x was put into the f function machine. If I want to find the derivative of h prime of x, that is the derivative of the outside function. See how f is the outside function where g is the inside function? G is being operated on. G of x is being operated on. There's some sort of mathematical operation going on to the whole function of g of x. So I want the derivative of the outside function, and I'm not going to change the inside function. It's the same. Then I'm going to multiply that by the derivative of the inside function. We're going to learn the chain rule exactly like we learned the product rule and the quotient rule. We're going to learn a verbalization of the chain rule. This is how you will always, always, always find the derivative of a composed function, no matter what that function looks like. Even next spring, when we are taking the derivative of some really crazy looking functions, you're still going to be able to use the chain rule using this verbalization. So make sure you know it. And it's just what I said a while ago. It is the derivative of the outside function, not changing the inside function. I copy the inside function down just as they gave it to me. Times the derivative of what's inside. There's the derivative of what's inside. That's how I'm going to verbalize using the chain rule to find the derivative of a composed function. Perhaps the best thing we can do is just take off and do some examples, and you'll get a better idea of how this verbalization is going to work. This says find f prime of x for f of x equal the composed function quantity 2x squared minus 4x plus 1, all raised to the power of 60. There is a function that's being operated on here. There was an entire function that was put into a function machine that raised whatever I fed it to the power of 60. It becomes really important that we can recognize the outside function and the inside function. The outside function was the last operation that was done when we put our independent variable into function machines. When I put x into function machines, the very first thing that was done to it is it was put into a machine that took 2 times whatever I fed it and squared it, minus 4 times what I fed it, plus 1. That is the inside function. that is the operation that happened first to the independent variable x when I fed it into the f of x function machine. The second operation, the last operation that was done, the outside, was that we took this result out of the first function machine and we fed that result into this function machine. That's how we got that for f of x. So we're going to have to become really adept at figuring out what's the inside function and what's the outside function. One of the easiest ways to do that is the inside function can be determined by asking a question. You want to ask yourself, what is being operated on? And by what, I mean what function. Of course, x is being operated on, but I want to know, has one function been put into another function machine? So when I look at a function, I ask myself, is anything being operated on? If something is being operated on, that requires the chain rule. Our questions are not going to be, find f prime for this function using this specific rule. You have to determine which rule is required. So if a function composition has occurred, if something is being operated on, that is a chain rule problem. The chain rule is verbalized as the derivative of the outside. There's the derivative of the outside. Not changing the inside. All of that times the derivative of what's inside. That's it. Now, we don't have to simplify that. We don't have to clean that up. If this were a multiple choice question, usually functions that have different operations in them are written as coefficients or constants first, and then we'll write factors in ascending order according to the power. So this is a linear factor of power 1. We would write it before we wrote this factor. So if this were a multiple choice question, your answer more than likely would look like this. They wouldn't simplify it any more than that. There's your first chain rule problem.